6, we're going to finish up our study of this chapter right now. We're going to start by talking about our first word problem. It says a colony of bacteria that grows according to the law of uninhibited growth. So you want to highlight this law right here, and that is this thing right there. And that probably looks pretty familiar, and that's because it's the same thing as your continuous interest formula, or compounding continuously. So this A naught right here, or A sub 0, that's the same thing as P. So that's your initial. E is obviously the same thing. Your R is still your rate. And then T is still clearly time, except for problems like this, the time span could be any unit. So for money, we usually use years, but for the law of uninhibited growth, your time could be anything from a day to a second to a minute. So it could be anything. Ultimately, it's very, very similar. So for letter A, it's to determine the initial amount of bacteria. Notice how they do give you the formula, and that's going to be very common here. So your initial amount is right there. So 100, we'll say like bacteria. You could also plug in 0. And notice how if you plug in 0 right here, that's e to the 0, which would be 1. So that's why it is in fact 100. The growth rate, all right, look right there. So that's your rate, 0.045. So let's convert that to 4.5%, meaning it's going to go up by 4.5%. If this were negative, it would go down. What's the population after 5 days? So we're looking for n of 5. So let's go to our calculator. 100, don't forget your times, e to the 0.045 times 5. There it is. We'll round to 2 places. 125.23, and it says grams, so we'll put grams. Okay, D, how long will it take for the population to reach 140? So this will take a little bit longer, so we'll do that over here. So we want the equation to equal 140 grams. So we'll write it like this. And we are solving for your time right here. So first thing you want to do is definitely isolate this thing. I'm going to put a box here for you. You're trying to isolate that. So let's divide by 100. So 1.4 should equal e to the 0.045t. Once we're in this situation, I'm going to natural log both sides, or write it in natural log form. And you can imagine this thing will come down if you want. Actually, I'll just write it out. Natural log e to the 0.045t. We hairball this thing. Natural log 1.4, 0.045 t times natural log e. Remember, natural log e is 1, so we just cross that out. And now I can divide by 0.045. And let's type that in a calculator. So natural log 1.4 divided by 0.045. There it is. We'll go to 7.48 days. And I knew it was days because right here, measured in days. E. What is the doubling time for the population? Okay, so if 100 is the initial, doubling would be 200 should equal 100 e to the 0.045 t. So this is an identical process, right? We're going to isolate this. And do the exact same thing. So 2 equals e to the 0.045 t. Let's make it a little faster. Natural log 2 equals 0.045 t. So t must be natural log 2 over 0.045, which, plug in your calculator, let's see. 15.4 days. All right, and that's our first example. Newton's law of cooling. So I gave this law to you right here. So we'll go through this together. But know that when we go through this, or if you ever see this in the future, I will give you this law, so you won't need to study or memorize everything and where it goes. I will give this information to you on a test or quiz if we ever need it. So let's first look at the question. An object is heated to 100 degrees Celsius and is then allowed to cool in a room whose air temp is 30 degrees. A. If the temp of the object is 80 degrees after 5 minutes, when will its temperature be 50? So essentially the law is talking about you have some object and it's hot, and then you put it in a room that's cool. What happens to that temperature? So in our minds, we understand logically that the temperature will cool, and this law is going to really break down mathematically what's actually happening. So the law right here says the temperature U of a heated object at a given time t can be modeled by the following function, this thing right here. T is a constant temperature of the surrounding medium, U sub 0 is the initial temperature of the heated object, and K is a negative constant. So essentially, this T and this T right here, that is your room temp, meaning you say surrounding medium, like the temperature of whatever you're putting the object into, the room of, or whatever it could be. U sub 0, that's your initial temp. And then U of T, that's your final temp. And then K is clearly your rate. And for these problems, we won't know the rate, so we often have to find it. So for letter A here, notice how it gives you this first piece of information. We have to deal with this first before we can even get to the second part. So this is actually a two-step question. Step one is we have to find the rate. So again, we can't even answer the question until we find the rate. So to do that, I'm going to copy this formula here and put it back. So that's the same formula as up there. And we're going to fill everything in. So the temperature of the object is 80 degrees after 5 minutes. We can actually use that. That would mean this object ended at 80 degrees, and T is the temperature of the room, which is 30. So right, 30 plus U sub 0, that's initial. So that's your initial right here. And again, the room temp is 30 because of this problem right here. 100 minus 30. And then E, we don't know K, but T is 5 minutes according to the problem. Now we're going to solve for K. So we're going to subtract 30. So 50 should equal 70 e to the 5k. Now remember, we have to isolate this thing right here. So I'm going to divide by 70. So 5 over 7 e to the 5k. Now I'm going to put this into log form. So natural log 5 over 7 equal to 5k. And k is equal to natural log 5 over 7 over 5. So at this point, we found the rate. So I'll highlight that. That's your rate. Now for questions like this, we actually have to have the exact value. So you want to make sure you do not round. We have to use the exact value of this expression. And to do that, we use our calculator. So we're going to go to natural log 5 over 7, and this is divided by 5. So this tiny number is our rate. And in order to use the exact value, we're going to store it. To store it, hit Shift, and then EEX right here. And you're going to see that it creates an answer with the arrow. That is going to store it into any letter we want. And I'm going to use k, so alpha and log, that's k, and it stores it. So anytime I call k in the calculator, it's going to repeat this exact value, which is fantastic. So in our note, in our homework, you just write this, triangle k, and that's going to mean stored in calc. Okay, so we got the rate. Let's draw a line. Now we have step 2. Answer the question. Answer the question. When will its temperature be 50 degrees? So exact same thought process. 50 is equal to, everything else is the same, because the room temp is still 30. The initial was 100 minus 30, then E, except now I have triangle K because I have the actual value, and T. So now we're solving for T, and remember, this is not a variable, this is a constant. This is this number right here. So now let's solve it. We're going to subtract, so 20 is equal to 70 e to the kt. Let's divide, and I'll put triangle there. Triangle kt, natural log 2 over 7 is equal to triangle kt. So t should be natural log 2 over 7 divided by triangle k. So let's go back to our calculator. Natural log 2 over 7 divided by k. There it is, 18.62 minutes. And that's how long it'll take this object to cool to that temperature. Okay, we'll do B, and C is really fast, so we're almost done. So B is saying, determine the elapsed time before the temperature is 35 degrees. So at this point, this is easy because you have the rate. Once you have the rate, all these problems are pretty much identical. So the final temperature is 35 degrees, and everything else is the same. The room temp is 30, the initial is 100, and then E to the triangle KT. Okay, so at this point, you kind of see the thought process here. So I'm going to go through it a little faster. 5 equals 70, e to the triangle kt. That's 1 over 14 equal to e triangle kt. So natural log of 1 over 14 divided by triangle k should equal t. Let's go back to our calculator. Natural log 1 over 14 divided by k. There it is, 39.22. Okay, and the last part, part C, it's kind of common sense. It says, what do you notice about the temperature as time passes? And so to keep it simple, as time increases, the object approaches room temperature, which makes total sense if you just think about it. An object would have to approach your room temperature over time. Okay, so that's it. Good luck on the questions, and I'll see you in class.